Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through all that you need to know for your upcoming test. So I'm going to divide the video into these sections here. So please let me know if you have any questions about it. We'll get straight into it, starting with linear. So we'll start with 2 points, minus 2 minus 9, which is down here, and 5, 12, which is over here. So let's join up these 2 points. So if I draw a line that starts at one point and ends at another, we call that a line segment. A line segment has a start and an end. So because it's got a defined length, we can find the midpoint of this line segment. We can find the point on this line segment that divides it in half. It'll be somewhere around there. So to find the midpoint of a line segment, it's very logical. All we do is find halfway between the two x values. So this is one, this is second x value, and then halfway between the two y values. So the midpoint is a point. So your answer, when asked for the midpoint, needs to have an x value and a y value. So in this case, we would add x1 and x2 together, divide by 2, and then we'd add the two y coordinates together and divide by 2. So it turns out you get 1.5 for the x value and 1.5 for the y value. So this point here would be about 1.5, 1.5, halfway between. Now, if I extend this line segment so it goes forever in both directions, that's what the arrows mean, goes on forever, it's not a line segment anymore, it is a line. We need to know how to find the equation of the line that passes through these 2 points. Now, it turns out the equation of any line can be written as y equals mx plus b. We call m and b coefficients. So all we actually need to do is find these coefficients m and b. So we follow these steps to do that. We first find m. That's the gradient, and we use the 2-point formula to find the gradients. This means y coordinate of the second point minus y coordinate of the first point, x coordinate of the second point, x coordinate of the first point. It's just rise, this is how far we've gone up, over run. This is how far we've gone across. When you found the gradient, you substitute it, x and y come from one of the points, substitute it all into this equation and rearrange to find what b is. So for the line that passes through these 2 points, so the gradient is y coordinate of the second point minus y coordinate of the first point over x2 minus x1. So just be careful here, we need 2 minuses. So this is 12 plus 9 over 5 plus 2. It's 21 over 7, which is equal to 3. So what I do now is I take my equation y equals mx plus b. I'm going to substitute m for 3. So that's the value I just found. Now, x and y come from one of the points. It doesn't matter which one. In this case, it'd be easy to use this point because both numbers there are positive. So I'm going to change x to 5. The x coordinate of this point that I've chosen is 5. So I've now got y equals 3 times x. I'm now going to substitute y. The y coordinate of that point I chose was actually 12. So I get 12 equals 3 times 5 plus b. This is a really easy equation to solve. So obviously, I can just write 3 times 5. Well, that's just equal to 15. So I have 12 equals 15 plus b. Subtract 15 from both sides. b is equal to minus 3. So the equation of this line is y equals m. So I'm going to rub out m and write 3 plus b. And I just figured out that b was equal to minus 3. So I'm going to rub that out. And now I replaced it with minus 3. The equation of this line is y equals 3x minus 3. So how would I graph something like this if I didn't already know? So I'm going to rub this out and show you how I would get the graph of y equals 3x minus 3. So when we have the equation in the form y equals something, the number in front of x is the gradient, and the other number is the y-intercept. So how we would graph this, we would just plot the y-intercept at -3, and the gradient is 3. So gradient of 3 means 3 over 1. This number tells you how far you go right. This tells you how far you go up or down. Because this is a positive, we go up. So we go 1 to the right and 3 up. So we go 1 to the right and 3 up will be there. So now that I've plotted 2 points, all I need to do is draw the line through them. And because it is a line now, not a line segment, I put arrows on the end to indicate it goes further in both directions. All right, let's now move on to quadratics. So just as I can find the equation of any line given 2 points through which it passes, if I'm given 3 points, I can find the equation of a parabola that passes through them. So we know that all lines can be written in the form y equals mx plus b. It turns out any parabola, its equation can be written in the form y equals ax squared plus bx plus c. Now, when we were finding the equation of a line, we just found each of the coefficients. And we're going to do the same here. We're going to find the value of a, b, and c. We're going to use these points to set up simultaneous equations to find a, b, and c. So c is actually really easy. This point here tells us straight away that c must be -20 because the x coordinate here is 0. If x is 0, this term and this term just equals 0. So you get y minus 20 equals c. So let's now substitute in this point to this equation. So we have y equals a times x squared plus b times x plus c, which was -20. So remember, whenever you're substituting a negative, make sure you have brackets when you put it in your calculator. So rearranging this equation, I get 22 equals positive 9a minus 3b minus 20. So of course, I can just add 20 to both sides, and I get 9a minus 3b is equal to 42. So that comes from the point minus 322. Now, if I substitute in this point, I get y equals a times x squared plus b times x plus c. So rearranging this equation, adding 20 to both sides, I get 12 is equal to 4a plus 2b. So I now have 2 equations that I will solve simultaneously. Now, I can't use the substitution method because neither the a nor the b is the subject of the equation. I need to use elimination. Elimination requires one of the pronumerals has the same coefficient in both equations. Now here it doesn't, so I need to multiply the equation. So if I multiply this top equation by 2 and the bottom equation by 3, they will then have the same coefficient. So when I multiply this top equation by 2, I need to multiply everything by 2. So I multiply 42 by 2, 9a times 2, minus 3b times 2. So similarly, when I'm multiplying the bottom equation, I multiply everything by 3. So now the b's in both equations have a 6 in front of it. So I can eliminate the b's by adding together these 2 equations, because minus 6b plus 6b is 0. So let's add everything in these equations. 84 plus 36, 18a plus 12a, and then minus 6b plus 6b is 0. So I've got 120 equals 30a. A is 120 divided 30, which is 4. So now I can substitute back into either equation. If I substitute into this bottom one, I get 36 is equal to 12 times a is 4, plus 6b, minus 12 is 6b, and of course, minus 2 is equal to b. So now I've found a, b, and c. Just like when I was finding the equation of a line, I'm done. Y is equal to ax squared plus bx plus c. So that's how you find the equation of a parabola given 3 points. Now let's look at how we would graph this parabola. So this is the parabola we calculated on the previous slides. Now to turn it into a graph, what we do is identify these 4 features, plot them, and then join them up. So the first feature is the orientation. If A, remember A is the number in front of x squared, is positive, it's a smiley face. If A is negative, it's a frowny face. Secondly, as I mentioned on the previous slide, the y-intercept is c. This constant term, when it's written in this form ax squared plus bx plus c, this number by itself is the y-intercept. Now, the real work comes in finding the x-intercepts. We let y equals 0 and solve the quadratic. And fourth, finally, we find the turning point, which is using this formula here. We then substitute the value we get for x into here to find y. So let's do that for our parabola. So here, a, number in front of x squared, is 4. That's clearly positive. So for this parabola, it will be a smiley face. So secondly, as I mentioned on the previous slides, the y-intercept here is minus 20, this value here. So thirdly, let's find the x-intercept. So we take our equation and change y to 0. So we are now solving this equation. So our 2 methods for solving, we can use the quadratic formula or factorization. So I will factorize this. So because it's a non-monic, because this is not 1, so what I have to do is use the AC method. So A, which is 4, times C, which is minus 20, gives us negative 80. So what I need to do is find 2 numbers that multiply to negative 80 and add to negative 2. So those numbers are minus 10 and positive 8. I use those 2 numbers to split up the middle term. So I get 4x squared plus 8x minus 10x minus 20. So now what I do is I factorize the first 2 and factorize the second 2 separately. So factorizing the first 2, highest common factor is 4x. So for the next terms, the highest common factor, I'll take out negative 10, and I get x plus 2. So you should get the same bracket here and here, otherwise you've done something wrong. So now we can use highest common factor again. The highest common factor of this and this is what's in the brackets x plus 2. And then what is left over? 4x minus 10. So here we can solve this by using the null factor law. The null factor law says if you have something times something equal to 0, either the first something is equal to 0, which means x is minus 2, or the second something is equal to 0. So if 4x minus 10 is equal to 0, add 10 to both sides, divide by 4, you get x is positive 2.5. So these are the 2 intercepts. Every parabola has 0, 1, or 2 x-intercepts. So finally, for the turning point, we use x is minus b over 2a. So in this case, b is minus 2, a is 4. So I get 2 over 8 or 0.25. So that is the x-coordinate of the turning point. It's also the axis of symmetry. The axis of symmetry would be the vertical line, x is 0.25. So because I only have an x value, I need to substitute into here to find the y value. A turning point needs an x value and a y value. So y will just be 4x squared minus 2 times x minus 20. So you can use your calculator for this. You get minus 20.25. So the turning point is 0.25 minus 20.25. So let's turn this into a graph. Okay, so now we've calculated all the features. We're just going to put it on our Cartesian plane. So we can't graph the orientation, but we can graph the y-intercept. So it will be down here at minus 20. So the x-intercepts, we had one of them at minus 2, the other one at positive 2.5, which will be about there. So the turning point was x is 0.25, which is about there. Y is minus 20.25, which will be down here. And so I just join them as so. We know because it's smiley face, it's going to go down, hit the x-axis, hit the y-axis, reach its turning point, and then it stops, turns around, and goes in the other direction. And there we have it. So now let's look at finding the point of intersection of a line and a parabola. So let's look at this question. Let's say we have this line y equals 10x plus k, and it's a tangent to the parabola we've just graphed. What is the value of k? So note, when we say something is a tangent, what it means is that this line and this parabola intersect once. If you have a line and a parabola, they can intersect 0 times, 1 time, or 2 times. Because remember, quadratic equations have 0, 1, or 2 solutions. So what I'm really saying is, what is the value of k such that this line and this parabola intersect once and only once? So this is how we calculate the point of intersection of a line and a parabola. We just let the line equal the parabola. Essentially, we're substituting this into this. We're replacing y with 10x plus k. So what we normally do is we would make one side equal to 0. We only know how to solve quadratics when one side is equal to 0. So what I'm going to do, make this side 0, I'm going to subtract 10x and also subtract k. So if this equation has one solution, then there will only be one point of intersection. If it had two solutions, there'd be 2 points of intersection. So I'm saying, what is the value of k such that this equation here has only one solution? So remember, there'll only be one solution if the discriminant is equal to 0. So that would imply that b squared, so b is minus 12, b squared minus 4 times a times c equals 0. So c is this term here. It's minus 20 minus k. So cleaning this up, I want this to equal 0. So I have 144 minus 16 outside of minus 20 minus k is equal to 0. So expanding the brackets, minus 20 times minus 16 is plus 320. Minus 16 times minus k gives us 16k. So to solve this equation, I'm going to subtract 320 and 144 from the left-hand side. I get 16k is minus 464. Divide each side by 16. You get k is minus 29. So that means that the line y equals 10x minus 29 intersects, it hits this parabola once and only once. So what would be the point of intersection in this case? So what would happen is, as I did before, make one side equal to 0 by subtracting 10x, and this time I'm going to add 29 to both sides. It turns out this is a perfect square. So if I wanted to find the value for x, I could factorize this using the AC method. Because I already did that, because I already factorized using the AC method, I'm going to use the quadratic formula this time. So to solve this equation, x is equal to minus b plus or minus the square root of the discriminant over 2 times a. Now I found, remember, the discriminant is equal to 0. I found that if k is minus 29, the discriminant is equal to 0. If you don't believe me, you can check that easily by doing b squared minus 4ac. So what I get is 12 minus 12 is positive 12, plus or minus 0 over 2 times 4, which is 8. So sorry, this value here, a, should have been 4. So 2 times a gives you 8. So the solution is x equals 1.5. And if I substitute that into the equation, I can substitute it here or here. It's obviously easier to do here. Y would be 10 times 1.5 minus 29, which is minus 14. So the line y equals 10x minus 29 intersects this parabola at one and only one point, which is 1.5 minus 14, okay? So I think we've done enough of parabolas, including solving. Let's now look at other polynomials. So it turns out that all linear functions and all quadratics are polynomials. Cubics are also polynomials. So we're going to look more now at polynomials. Any polynomial is also a function, but I'm going to go through functions later in the video. So when we're using polynomials, we often use fx notation. So a polynomial has lots of x's in it, but it only has positive integer powers of x. So if I have something like x cubed plus 1, that is a polynomial, because the only power of x here is a positive integer. If I have something like fx equals, let's say, x to the power of 4 minus the square root of x plus 2x squared or whatever, that's actually not a polynomial. X to the power of 4 and this term here, these two terms, the power of x is a positive integer. But the square root of x makes it not a polynomial, because the square root of x is the same as x to the power of a half. It's only a polynomial if the powers of x are positive integers. So this is not a polynomial. So for this polynomial, there's some terminology we need to know. So the degree of the polynomial is the highest power of x. So here, the highest power of x was 3. So the leading coefficient is the coefficient of the highest power of x. So in this case, the highest power of x was x cubed. The coefficient is actually 1 if it's not written. So the leading coefficient of fx is 1, and that means the polynomial is monic. If the leading coefficient is 1, the polynomial is monic. If the leading coefficient is not 1, then the polynomial is non-monic. And we just use that terminology because monic polynomials are so much easier to work with. So this fx notation allows us to perform substitutions really easily. So for example, if I substitute in f of minus 1, that means I take my polynomial and exchange x for minus 1. So f of minus 1 for this polynomial here would be x cubed, so x is minus 1 cubed plus 1. So if you put that on your calculator, you actually get 0. So what that means by the factor theorem is that x plus 1 is a factor. So it's the negative of what you substituted. So if f of 2 equals 0, then x minus 2 would be a factor. So that's really important. What that means is I will be able to write f of x as x plus 1, this factor, times some other polynomial. And that's really important for solving polynomial equations. So that's the main thing that we are doing with cubics and higher degree polynomials. We're factorizing them using the factor theorem, remainder theorem, and polynomial long division. The factor theorem tells us that this is a factor, and then polynomial long division can help us find this polynomial here, what I multiply by to get x plus 1. So we're now going to look at another example of this. So let's look at this question here. We're going to find the value of k if this polynomial divided by this polynomial leaves a remainder of 6. So the remainder theorem tells us the remainder, when fx is divided by x minus 2, the remainder is just equal to f of 2. So similarly, the remainder when this is divided by x plus 5 is f of minus 5. That's the remainder theorem. Make sure you know it. So I'm going to substitute in x for 2. So I get 2 cubed minus 6 times 2 squared plus 5 times 2 plus k, right? So because the remainder is equal to 6, the claim here is that this polynomial, when I substitute x for 2 into this polynomial, the answer is 6. That's what the remainder theorem says. So 2 cubed is 8, so I get 8 minus 24 plus 10 plus k is equal to 6. So solving this equation, we get k is equal to 12. That's a pretty easy equation to solve. So now I have my polynomial x cubed minus 6x squared plus 5x plus 12. So when I divided by x minus 2, the remainder was 6. It was not 0. So that actually means x minus 2 is not a factor of this polynomial fx. So how would I find a factor? Well, what we need to do in order to factorize this polynomial is we need to find one factor and then use polynomial long division. So a factor of this, if I don't know any, what I do is try positive and negative factors of this number here. I substitute those numbers for x and see which makes them equal to 0. So I only need to come up with one factor. So I'm not obviously going to try f of 2 because I know that x minus 2 is not a factor. But let's try something else. Let's try f of 3. So if I substitute x for 3, I get 3 cubed minus 6 times 3 squared plus 5 times 3 plus 12. And putting that in my calculator, I get 0. Because f of 3 is equal to 0, this means x minus 3 is a factor. Now, that means that I can write fx is equal to x minus 3 times some polynomial. As I said before, the factor and remainder theorem don't tell us what this polynomial is, what can be times by x minus 3 to get fx. To find this, I need to use polynomial long division, and that's what I'm going to do now. So what we're doing when we're doing polynomial long division is we're actually constructing this polynomial, figuring out what the coefficients are. So I know that because this is a linear function and this is a degree 3 polynomial, what goes in here, it must be a degree 2 polynomial. So it'll be something times x squared plus something times x plus something. I just need to find out what goes in those boxes, and that's what polynomial long division does. So this is how we start polynomial long division. We go leading term divided by leading term. So x cubed divided by x is x squared. So what I've actually just figured out is that this first term here is an x squared term, or 1x squared. So the problem is, when I go and expand this, if I go minus 3 times x squared, I would get minus 3x squared. I wouldn't get minus 6x squared, which is what I want. So whenever you get a term up here, you multiply by the linear term. So we go x squared times x squared times minus 3. So then we subtract to find the remainder. So minus 6 minus minus 3 gives us minus 3x squared. Whenever you found the remainder, what you do is divide it by the leading term. So minus 3x squared divided by x gives you minus 3x. So I figured out that minus 3 goes in this term here. So the reason this works, when I multiply minus 3 by x squared, I get minus 3x squared. Now, when I multiply x by minus 3x, I get another minus 3x squared. Minus 3x squared plus minus 3x squared gives me minus 6x squared. So when I expand this, I'm going to get a minus 6x squared term like I wanted. So whenever you've calculated something up here, remember what you need to do is multiply it by the linear term so we can calculate the remainder. We're just following the process again. So I bring down this 5 so I can compare it, calculate the remainder. So minus 3x times x gives you minus 3x squared. Minus 3x times minus 3 is positive 9x. So now we calculate the remainder by subtracting. So I go 5x minus 9x is negative 4x. Whenever you've got a remainder, which I do here, I divide by the leading term. So minus 4x divided by x gives me minus 4. I've figured out that minus 4 is the last term here. It's x squared minus 3x minus 4. So once again, the reason I needed to do that was because when I times x by minus 4, I get minus 4x. Minus 4x plus 9x will give me 5x. So I'm now going to calculate the remainder of the whole thing. So I bring down this 12. So I bring down this positive 12. Remember, whenever I get a number up here, I times by the linear factor. So I times minus 4 by x gives me minus 4x. And minus 4 times minus 3 is positive 12. So now, if I subtract again, the remainder I get is 0. There's a 0 left over. That final number is the total remainder. So 0 is what I expected, because I know that x minus 3 is a factor. So when I divide this by this, there should be a 0 remainder. Just like 4 is a factor of 36, when you divide 36 by 4, there's no remainder. When I divide this by x minus 3, there's no remainder. So I know I've done something right. So what I've actually figured out is that fx, this polynomial here, is equal to x minus 3 times x squared minus 3x minus 4. So I've got this here is the same as that there. So what I can do is I can now factorize this quadratic here easily. I just need to find two numbers that multiply to negative 4 and add to negative 3. So I've now split fx into 3 linear factors. Note, a degree 3 polynomial can never have more than 3 linear factors. Similarly, a degree 4, a quartic, could never have more than 4 linear factors. So I've factorized it. So if I wanted to solve fx is equal to 0, if I wanted to solve the equation x cubed minus 6x squared plus 5x plus 12 is equal to 0, I can now just use the null factor law. Either the first thing is equal to 0, the second thing is equal to 0, or the third thing is equal to 0. And then I'm done. All right, the last thing we'll do, we'll go through hyperbole and circle and what a function is. So a hyperbola, plural hyperbole, is a graph of this form y equals a over x plus b plus c. So this graph is different than the graphs of polynomials. Hyperbole are still functions, but unlike polynomials, they're not continuous. Hyperbole have asymptotes at x equals the negative of whatever this number is and y equals whatever this number is. They are no-go zones for the graph. And this value a on top can determine whether the hyperbola lives in the top right, bottom left quadrants or top left, bottom right. Probably doesn't make a lot of sense, so let's go through an example. So let's now graph this function y equals 1 over x plus 2 plus 3. So we start by looking at the asymptotes, the no-go zones. So the no-go zones, we have x equals minus b, the negative of what's on the bottom here. So that'll be x is minus 2. So why is this a no-go zone? Well, x cannot equal minus 2, because if I substitute x for minus 2, I get 1 over 0. It's undefined. You cannot divide by 0. So this graph can never have an x value of minus 2. So there's also another asymptote. So this fraction can never equal 0. You can't divide 1 by a number to get 0. So because this fraction can't equal 0, y cannot equal 0 plus 3. So that means y equals 3 is another no-go zone for this graph. Y can never equal 3. So there can be no points on the hyperbola where x is minus 2 or y equals 3. So let's graph these asymptotes. So x equals minus 2 is a vertical line through minus 2. So this is not the graph of the hyperbola, this is an asymptote. The graph can never hit that line. So similarly, y equals 3 is an asymptote. It's perfectly vertical. The hyperbola can never hit this horizontal line either. So now we look at the value of a, the value on top of the fraction. So see, using these asymptotes, they've sort of divided it into 4 quadrants. Here, 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 and here. Top right, top left, bottom right. So if a is positive, the hyperbola lives here and here. If a is negative, it lives here and here. A is clearly positive, so the hyperbola will live here and here. So what happens with hyperbola is they sort of hug, they get closer and closer to you, but never actually hit the asymptotes. So to get closer and closer to the asymptote and closer to the asymptote. The graphs of hyperbola sort of occur in 2 pieces. They get closer and closer to the asymptotes, but never hit them. So if I wanted to find intercepts, as you're asked to do, we just follow the rules that we have for other graphs. So if I want to find the y-intercept of this hyperbola, I just let x equal 0. So then the y-intercept would be 1 over 0 plus 2 plus 3. That just gives you 3.5. So this intercept here would be at 3.5. That's the y-intercept. If you wanted to find the x-intercept, you let y equal 0. So I get something like this. Then I would subtract 3 from both sides. Now what I do is I can move the 1 and the fraction line over here. So I would get minus a third is equal to x plus 2, and I would subtract 2 from both sides. So that will give me x is equal to minus 2 and a third. So that means this value here, where it hits the x-axis, would be minus 2 and a third. And that's all there is to graphing them. So make sure you can also find the equation of a hyperbola. So I give you the graph of a hyperbola and you tell me what the equation is. We'll do that now. So let's find the equation of the hyperbola in this graph here. So I know the equation is going to be y equals a over x plus b plus c. So all we need to do is find the values of a, b, and c, and we've got the equation. So remember I said that the asymptotes were at x equals minus b and y equals c. So here you can see clearly the asymptotes are x equals 2 and y equals minus 2. So the equation of this is going to be y equals a over x minus its asymptote, and then the y asymptote stays the same. Okay, so remember, the reason it's x minus 2, if I substitute x equals 2, I'm dividing by 0. That's why 2 is a no-go zone. Also, y equals minus 2, this fraction cannot equal 0, so y cannot equal 0 minus 2. Okay, so once we've got the asymptotes, we just need to find the value of a. So we're going to find a by substituting in a point that lies on the hyperbola. So we have this point here, minus 1 as the y-intercept. So I'm going to substitute y for minus 1 and x for 0. So I've now got this equation to solve. So I'm going to add 2 to both sides. Now timesing each side by negative 2 gives us a is negative 2. So this hyperbola is going to be y equals a over x minus its asymptote plus the other asymptote. Okay? And remember, as I said before, if a is negative, the hyperbola is in the top left, bottom right. So we expected a negative value for a because it was in these 2 quadrants, unlike the previous hyperbola, which was in those 2. So let's quickly look what would be the domain and range of this hyperbola. So the domain of any graph, whether function, polynomial, or not, The domain is the set of values x can take. The range is the set of values y can take. So if we look at this graph here, so for the domain, it's the set of values x can take. So x can take any value except 2. So when we're writing the domain, we need these squiggly brackets because it's a set of values. So we write the set of x values such that x does not equal 2. So that's another way of saying x can take any value except 2. So similarly for the range, we see y can take any value except -2. That's the only horizontal line the graph won't hit. So the range is a set of y values such that y does not equal -2. So that's what domain and range means. So the last thing we're going to do here, we're going to look at circles. So believe it or not, this is actually the graph of a circle. It doesn't look like it's in the form that we're used to for circles. So I can put it in that form by completing the square. So I'm going to complete the square with the x's and then complete the square with the y's. So remember, for x squared minus 10x, it looks like a quadratic. So the coefficient of x squared is 1. And this coefficient here I refer to as b. b is -10. So what I want to do is I want to add a number on here. So I can write this as x plus or minus something squared. I want to make this a perfect square. So what number goes in here is half of b on 2. So b is -10. So the number I want to put in here is -5. So I want to make this into -5 squared. But if I were to expand this, I'd get x squared minus 10x plus 25. -5 squared is 25. So I want to add that onto the end there. So similarly for the y's, even though it's a y this time, we do the same process. We treat this as our b. I want to write this as y plus b over 2 squared. The problem is, when I expand this, I would get y squared plus 24y plus 12 squared plus 144. So what I want to do is add another 144. That's b over 2 squared. So I can't just add 25 and 144 as I please. So what I'm essentially doing is I'm adding 25 here, so that this is a perfect square. Then I'm adding 144 here, so that this is a perfect square. So these equations still balance, I need to add 25 to this side and 144 to this side. So I actually need to add 169 to the right-hand side. So I've added 169 to the left-hand side, so I must also add it to the right-hand side. So what I have, just to be clear, x squared minus 10x plus 25 plus y squared plus 24y plus 144 is equal to 169. So by completing the square, I'm able to write it like this. X minus 5 squared plus y plus 12 squared is equal to 169. This is in the standard form for a circle. So if you have an equation of the form x plus a squared plus y plus b squared equals some other number squared, that is a circle. Its center is the negative of the two numbers. So negative a, negative b. So this number has to be the one with x. It's the negative of the number with x. This is the negative of the number in the brackets with y. So the radius of this circle is equal to r. It's actually equal to the square root of this number. So, because I've written it in proper form, I can easily find what the center and radius are. The center would be 5 minus 12. The radius is not 169. It's the square root of 169, which is 13. So let's now graph this circle. So we mark here the center of the circle at 5 minus 12. Remember, it's the negative of this is the x-coordinate, and the negative of that is the y-coordinate. So we found in this case here, the radius was equal to the square root of 169, which is 13. So we have the center of the circle at 5 minus 12. The radius 13, so go 13 in each direction. So we go 13 over here to x is 18, and I'll just put a little dash there. Then we go 13 over this way, so 5 minus 13 will go to minus 8, and I put a little dash over here. So now I'm going to do the same in the other direction. So from the center, it's going to go 13 up. So it's at minus 12 for y at the moment, so it's going to go up to 1. And so I'll just put a little dash there. And it's also going to go 13 in this direction down here. So it's going to go down to y is minus 25. Again, I put a dash there. So when you've got those 4 points and the center, it's really easy. You just draw a circle. So I apologize that my circle drawing isn't very good, particularly on this iPad. It should be a perfect circle. Of course, when you're doing it by hand, you're never going to get a perfect circle. But this is what the graph will look like. So anything in the form x plus a squared plus y plus b squared equals a number, that is a circle. Center minus a minus b, square root of this gives you the radius, and we graph it just like this. So even though this didn't look like it was in that form, after we use completing the square, we put it in that form. So it turns out circles are different to hyperbola and any polynomial we've graphed because they are not functions. The reason they're not functions is they fail the vertical line test. So the vertical line test is if I draw any vertical line, if it hits the graph more than once, it's not a function. So up here says what I just said. So circles are not functions because I can draw a vertical line that hits the graph more than once. So here it actually hits the graph twice. So if I were graphing a parabola that, say, looks like this, that is a function because I can't draw a vertical line that hits this graph twice. Anywhere I draw a vertical line, it will only hit this graph once. So parabolae, or any parabola, is a function. In fact, any polynomial is a function. So that means all linear functions, all parabolas, all cubic graphs, all quartics, they are all functions. So it's the same for hyperbole. So if I have a graph of a hyperbola like this, it is never possible for me to draw a vertical line that hits the graph more than once. Any vertical line I draw hits the graph only once. That's why hyperbola, like polynomials, are always functions, but circles are never functions. So if I had some weird looking graph like this, this is still a function because it passes the vertical line test. If I have something like this in red, that is not a function. So the blue is a function, the red is not a function. The red would fail the vertical line test because I could draw a line that hits it there. But the blue would always pass the vertical line test. So finally, back to our circle here, we can calculate its domain and range really easily. So of this circle here, remember the domain is the set of values that x can take. So here, x can take values from minus 8 to 18. So from the center point, it went 13 this way and 13 this way because 13 was the radius. So x can take any value between and including minus 8 and 18. So we write it like this. X is between and including minus 8 and 18. So that's the domain, the set of values that x can take. So if I look at the range, the set of values that y can take, I see that y can take any value between including minus 25 and 1. So from the center point at minus 12, it can go 13 up and 13 down. So the range would be y is between and including minus 25 and positive 1. So domain and range done. All right, sorry for the long video. Thank you so much for tuning in. This has been the luckiest maths teacher in the world. Look forward to seeing you acing the test. You're a superstar.